Nature is not only stranger than we imagine, it is stranger than we can imagine. J.B.S. Haldane. Watch until the end. The most counterintuitive anatomical fact appears in the final section. Acanthonus spiniger is frequently described as one of the deepest living bony fishes ever recorded. It inhabits abyssal depths exceeding 3,000 meters, where hydrostatic pressure surpasses 300 atmospheres and light is completely absent. At first glance, it appears fragile, almost unfinished. That perception is accurate. Acanthonus spiniger possesses one of the most weakly ossified skeletons among vertebrates. Its bones are extremely reduced in density. The body contains a high proportion of gelatinous tissue, decreasing overall density and improving neutral buoyancy in extreme depths. This is not degeneration, it is optimization. In high-pressure environments, heavy calcification is metabolically expensive and structurally unnecessary. Reduced skeletal mass lowers energy demand. In abyssal ecosystems where food input is sporadic, energy efficiency determines survival. The body is elongated, soft, and somewhat flaccid compared to shallow water relatives. Fins are delicate. Muscle mass is moderate but adapted for short, controlled movements rather than sustained swimming. Its feeding strategy is opportunistic. It consumes benthic invertebrates and small organisms encountered near the seabed. Ambush and slow hovering dominate its behavioral profile. Midway through this examination, recall Darwin's structural logic. It is not the strongest of the species that survives, nor the most intelligent but the one most responsive to change. Charles Darwin. Acanthonus spiniger did not evolve armor, it evolved minimalism. Here is the overlooked structural detail. Its reduced skeletal ossification is accompanied by modifications in connective tissue composition, maintaining structural integrity under pressure without the need for dense bone. The surrounding water pressure effectively supports the body. In shallow water, such a structure would collapse or deform. At depth, it is stable. The absence of swim bladder dependence further stabilizes buoyancy control. Many abyssal fishes rely on lipid storage and gelatinous tissues rather than gas-filled organs, which are inefficient under extreme compression. Now about the featured product. Acanthonus spiniger product is an in-depth marine biology resource dedicated entirely to this extraordinary abyssal fish. It explains skeletal reduction, pressure adaptation, buoyancy mechanics, metabolic strategy, and evolutionary context. The material is structured for marine enthusiasts, educators, and content creators seeking accurate scientific breakdowns of extreme environment vertebrates. The product analyzes anatomical diagrams, environmental constraints, feeding ecology, and abyssal survival strategies. It can be used as an educational reference, research supplement, or documentary preparation material. The link is available in the description. Returning to biology. The boneless fish label often used in media is technically incorrect. It remains a vertebrate. It possesses bones, but dramatically reduced in density and rigidity. This distinction matters. The species demonstrates that vertebrate design is not fixed. It is conditional. Under extreme hydrostatic pressure, rigidity becomes less important than energy economy. In abyssal ecosystems, excess structure is waste. If this analysis clarified how extreme pressure reshapes vertebrate anatomy, support the channel. Subscribe for precise deep-sea breakdowns, like the video to help distribute accurate marine science, and comment which abyssal species should be analyzed next. Your engagement directly funds further structured research content.